Hi, class. Welcome back. Let's take a look at the next part of neurology, where we're going to be talking about different parts of the brain that are involved with protection of the brain. So, the bone, obviously, the skull itself is going to protect the brain. We learned about cranial bones in Anatomy and Physiology 1, where you had like the frontal bone, occipital bone, parietal bone, temporal bone, the vertebrae, right? So bone obviously is a shield that protects the brain. We have meninges. The meninges are three main layers that we have around the brain, and it's the same three layers that also protect the spinal cord, and it's called the dura mater, the arachnoid, and pia mater. And this is from the pia mater is the most internal layer, and the dura mater is the outermost layer, and the arachnoid is in the middle. Okay, so the meninges are around the brain, and they are around the spinal cord. And then we have fluid. The fluid that we're talking about is called cerebral spinal fluid, CSF. And remember, those are made by a microglial cell called an ependymal cell. The ependymal cells make cerebral spinal fluid. And they are lining, the ependymal cells line the ventricles. So if we look in the center of the brain, let's see if I can outline it. I'll change it to red. So what we have here, those are the ventricles. There are these chambers, and all throughout the ventricles, whether it be the lateral ventricle, and there's two of them, one, two, one in each hemisphere. So there's one ventricle, two ventricle, here's the third ventricle, number three, and the fourth ventricle is down here, that's four. So there's four ventricles, and lining the ventricles are going to be ependymal cells, all produce cerebral spinal fluid. So you're going to have bathing fluid on the inside, but then there's this escape, and it can circulate all around the brain as well. So we have fluid inside and outside that help cushion and buoy the brain against any type of impact. Okay? And the CSF happens to float in a layer that's deep to the arachnoid called the subarachnoid space. The subarachnoid space is the layer of which CSF is constantly flowing. Okay, how does the brain get its nutrients and get its oxygen? It gets it from blood flow. And we are going to have several lectures on the cardiovascular system, but we're just going to introduce the blood flow to the brain is coming from main arteries that come off of the heart, one being the vertebral artery, which is here, vertebral, going through the vertebrae, through the transverse foramen, and then the second being the carotids, especially the internal carotid that goes into the brain. And then after the oxygen and the glucose is brought to the brain and it becomes deoxygenated, it has to find a way to drain from the brain and get back to the heart. And that's where it's going to use the jugular veins. Okay, that's coming down back to the heart. The brain utilizes about 20% of the body's oxygen supply. And if there's any interruption of the blood flow or any interruption of oxygen, then that's what we call, if it's temporary, we call it a transient ischemic attack, or we call it, if it's a big one, we call it a stroke. right? And that can result in permanent damage to the brain and death of the brain cells. If there's temporary loss of glucose, then that can result in some mental confusion, dizziness. People can go unconscious. But if you lose glucose and oxygen for an extended period of time, then brain cells start to die. Okay, the brain and the neural system needs fuel, it needs oxygen, and it needs motion for survival. Fuel is glucose. So the body needs glucose, oxygen, and movement in order to thrive and survive. When you deprive the body of glucose, oxygen, and movement, then the neural system starts to degenerate and break down. Here is the blood supply, and we can see the vertebral arteries, and we can see the carotids. The vertebrals and the carotids, these are two backup systems where if a vertebral gets clogged, we can still get blood into the brain to a carotid. If a carotid gets clogged, we could still find a way to get blood through it through the vertebrals. And there's a circle right here in the middle. So when we learn about the circle of Willis, the circle of Willis is the circle that exists right here that finds a way of creating blood supply to all the different parts of the brain. And again, we'll cover that mostly when we get into the cardiovascular system. All right, let's look at the CSF, the cerebral spinal fluid, from the lateral view. We're taking a look here, what's in the center, these ventricles, the four ventricles, but now we're going to be looking at it from the lateral view. So from the lateral view, we can see the lateral ventricles, and there's two of them. One, two. One is in each hemisphere. One's in the right cerebral hemisphere, the other is in the left cerebral hemisphere. So we have two lateral ventricles, and the CSF has to flow from ventricle 1 and 2 into the third ventricle. And the way it gets there, it has to drain through this plumbing, through this piping right here, which is called the interventricular foramen of Monroe. So how does the CSF go from lateral ventricles 1 and 2 into the third ventricle? It's got to get there through the interventricular foramen of Monroe. Then the CSF is in the third ventricle, and now it's got to find its way into the fourth ventricle, which is down here. Now it's got to go through another drainage duct, which is here. That drainage duct is called the cerebral aqueduct. Sometimes it's called the aqueduct of Sylvia or Sylvis. Now it's in the fourth ventricle, and now it can escape and surround and bathe the brain and the spinal cord. So it can go down the spinal cord through the central canal, or it can escape into the lateral or the median aperture, the lateral or the median aperture. And it helps to circulate around the brain and spinal cord. CSF, look at this, your body has around 3 to 5 ounces of it. It's a clear liquid. It's got glucose, proteins, and ions, and its functions are mechanical protection, chemical protection, and circulation. From a mechanical perspective, it's going to buoy and float the brain to soften impact against TBIs, traumatic brain injuries. Chemical protection, it's involved in action potentials, nerve conduction, and circulation. It's involved in nutrients and waste product removal. So there's something called glymphatics, not lymphatics, but glymphatics. It's something that was discovered just a few years ago, and it's a flushing system of the brain. And you need 7 to 8 hours of sleep in order for the brain to flush itself and clean itself out. If you don't get 7 to 8 hours, you can wake up with lots of brain fog because the lymphatics didn't get to do its thing. Okay, give me just 1 second here. Okay. Now, when we look at the origin of the CSF, remember the origins, what's producing them, they're produced in the choroid plexus. They're produced in the choroid plexus, but the choroid plexus is just a group of capillaries that are covered by ependymal cells. So it's these ependymal cells that are producing the CSF, and they're located in the choroid plexus. And again, in this picture, we can see the lateral ventricles 1 and 2. We can see the third ventricle. It drains here through the interventricular foramen of Monroe. After the third ventricle, it's got to get into the fourth ventricle, where it goes to the cerebral aqueduct of Sylvius, and then it can drain down and protect the spinal cord if it goes through the central canal. And the central canal, if I draw a cross section of the spinal cord and I draw that butterfly, that hole right in the center, that is the central canal. Otherwise, it escapes through the lateral aperture and median aperture. Again, when we look at the brain, look at that cross section, we could see the lateral ventricles. The choroid plexus is lined with ependymal cells. Okay, so here is the choroid plexi, and we can see the ependymal cells. All of these are ependymal cells, and they're going to produce CSF, cerebral spinal fluid. Again, just another look from a different perspective. Here's your lateral ventricles 1 and 2. Here's your third ventricle, and here's your fourth ventricle. In order to get from the lateral ventricles into the third ventricle, it's got to go through the interventricular foramen of Monroe. To go from the third ventricle into the fourth ventricle, the cerebral aqueduct of Sylvia. After the fourth, it goes down the central canal, which is here. That's the central canal, or it can go through the median aperture or the lateral aperture. Okay, and this is just the flow chart that shows what we just said, right? Lateral ventricles, which is 1 and 2. Here's the third ventricle. Here's the fourth ventricle. There's the interventricular foramen. Here's the cerebral aqueduct. And then we could see that it goes through the lateral and median apertures, and it's bathing and circulating in that subarachnoid space. And then it gets reabsorbed in the arachnoid villi of the dural venous sinus, which is way up at top, right? It's way up at top. Let me see if I have a picture of it. Right here, the superior sagittal sinus, right up in here, gets reabsorbed. Oh, here it is. Great. So we can see the reabsorption of it way up at top. It's reabsorbed through these arachnoid villi. It looks like these grape-like clusters that we see on the top here. Okay, the arachnoid villi is where the CSF gets reabsorbed. All right, and it's up in that superior sagittal sinus, way up at top, right in here. And it should be reabsorbed at the same rate that it's produced, right? That makes sense. Your body is making it, then it should be reabsorbed. Otherwise, if there's a blockage of it, we can get, and a blockage of that CSF can happen from a tumor, infections, inflammation, meningitis, some sort of hemorrhage or injury. It can create hydrocephalus, which is water on the brain. And when that happens, you start to get this swelling, this huge inflammation. And then they have to create this drainage shunt where a neurosurgeon implants a drain, shunting the CSF out of the head into the veins of the neck or the abdomen, right? Because the pressure in newborns, the fontanelles allow the internal pressure. It causes expansion on the skull, and we don't want it to damage the brain. Okay, so they have to shunt that fluid out of there. That's called hydrocephalus. So cerebral aqueduct, it's very faint, but you can see right there That orange structure right there is the cerebral aqueduct. Okay, good place to take a break here.